Hello, welcome to my talk. This talk is on water waves in finite water depths. Part 1, Wave Equations and Solutions. In this talk, I will introduce how the equations are established for water waves and how we can find the solution for the water wave in finite water depth. And you will see how the waves are changing from deep water to shallow water, including, in this part, the changes of the wavelengths and the wave velocities. For the problem, a global fixed Cartesian coordinate is used. The origin will be fixed on the still water level as z equaling 0, and it points up positively. As such, the wave elevation on the free surface can be expressed by z equaling to eta 0. X is pointing to the wave propagation direction. This is used for simplifying the problem. The wave component can be regarded as a 2D wave, which is only dependent on x and z. Generally, we can assume the fluid is irrotational and incompressible for water wave. Therefore, the Laplace equation is the equation for wave potential function phi x z t, given by this Laplace equation. Under the assumption of an irrotational and incompressible flow, the conventional unsteady Bernoulli's equation is satisfied, given in a general form as this. Here, C0 is the integral constant, and it can be chosen for different constants based on different situations. Here, we choose C0 equals P0, the atmospheric pressure, and this can be justified when we reduce the wave amplitude to 0 to the calm water. And in this case, we can see the corresponding velocity potential function phi would be 0 or a constant. And at z equaling to 0, the pressure is the same as the atmospheric pressure P0. So we have the Bernoulli's equation for the problem of water wave. To solve the wave potential function, we must specify the relevant boundary conditions. The first boundary condition is the seabed condition, given as this, meaning that the vertical fluid velocity is 0 at the seabed for z equaling to minus h. This can be understood. There is no penetration of the fluid through the seabed, that is, no penetration seabed condition. On the water surface, we have the climatic boundary condition, given as this at z equaling to 0. This equation means we have two different ways to calculate the vertical velocity. Mathematically, we can calculate the vertical velocity using the wave potential function phi as this, and we can also calculate the vertical velocity given by this, the physical vertical velocity. If you would like to see how this equation is derived, please refer to my talk on linear wave theory. The dynamic boundary condition can be easily obtained by linearizing the unsteady Bernoulli's equation at the free surface, P equaling P0, given in this. So if we put these two free surface boundary conditions together, we can obtain the equation as this, at z equaling to 0. This is a typical wave equation, and it implies the water surface has a form of a wave. Since the free surface is given in an equation of a wave, so it can be deduced that the 2D wave can be expressed as a generic form of wave on the free surface as eta 0, given as this form. Here, A is the given wave amplitude, omega is the wave frequency, and K is the wave number. From this expression, we can obtain a wave form when we fix the variable t. We can imagine we take a snapshot of the wave. So from the record, we can see the distance between two joint peaks. Here is the wavelength lambda. We can also fix the x. This means we watch the wave or measure the wave at a fixed point. From this record, we can obtain the wave period, the time lapse between two joint peaks. Here, we may ask a question. If we have an expression of the water surface given in this form, then why we need to study the water wave further? The answer for this is that from this expression, for a given wave amplitude and the frequency omega, these two parameters are the normal input for a given wave. However, we don't know the relation between the frequency and the wave number. And the question is how we can calculate the wavelength, wave phase and the group velocity, the water particle motion, wave energy, etc. This is why we need to link this wave expression to the wave velocity potential function, and from which we can obtain all information about the wave. For simplified mathematical analysis, we can write the wave elevation in this form, following the Euler's formula as this. However, we must remember the actual value of the wave elevation is the real part of this expression, can be seen here. So the real part and the expression is this. So this expression is the same. For the 2D Laplace equation, we can assume a generic solution expressed as this. So if we substitute the expression into the Laplace equation, we can easily derive this equation for the new variable capital Z as this. This derived equation would have a general solution as this. So if we substitute this expression into this derived equation, it would be satisfied automatically, regardless what the constant c and the constant d are. So next, we need to determine the constants c and d using the relevant boundary conditions. We examine the seabed condition here. The long penetration seabed condition is given as this. The vertical velocity at the seabed is 0. Substitute the general velocity potential function into this seabed boundary condition. We have the expression as this and this. To ensure the seabed condition, this part must be 0. Hence, we can obtain the relation between the constant c and the constant d as this. Therefore, the velocity potential function can be written in this form. Now here, only the constant c needs to be decided. In this slide, we apply the free surface boundary condition. From the dynamic surface boundary condition, we have the wave elevation expression. After using the velocity potential function, we have expression as this, eta 0 given in this form. If we compare the wave elevation on the surface, the general form eta 0 in this, hence we can obtain the constant c given in this. So now we can obtain the velocity potential function in the finite world depths given in this form, and we have the expression as this. How this part is derived, we can see this mathematical derivation step by step. So this is the velocity potential function for a wave of amplitude a and the frequency omega in the water depth h. If we compare this velocity potential function to the wave velocity potential function in deep water, we can see the difference between these two velocity potential functions. And here we use a subscript 0 to indicate the physical parameters in deep water. And these two expressions would be same if we take the water depth h, it's infinite or large enough to be considered as a deep water. In this slide, we'll use the wave surface boundary condition, which was derived in the previous slide, given in a partial differential equation as this. If we substitute the velocity potential function into this boundary condition, we can obtain a relation called the dispersion relation, given in this form. This relation links the wave frequency omega and the wave number k. If we compare this dispersion relation to that in deep water, we can see the difference. The dispersion relation in the finite world depths is much more complicated than that in the deep water, since in deep water, tanh kh would be close to 1 when h is large enough. From the dispersion relation, we can conclude the longer period of a wave, the faster the wave travels until it reaches the extremely shallow water. If the water waves are of colors for different frequencies as those in light, then the different colored wave could travel in different speeds. Therefore, the colors would be separate in the wave propagation. This is the physical meaning of dispersion. Use the dispersion relation for finite water depths. We can derive an equation for calculating the wavelength lambda. Based on the relation between the wave frequency and the period, and between the wave number and the wavelength, we have relation as this and this. Here, lambda 0 is the wavelength in deep water. Calculate in this formula. This equation for the wavelength in finite water depths is a nonlinear equation. There is no analytic solution for this equation, but the approximation method for the wavelength in the finite water depths have been proposed by many researchers. The details can be found in the reference. More accurate method for calculating the wavelength is the iterations of the equation. Here, we calculate the wavelength by iterating 100 times of the equation. We can see the wavelengths of different wave periods in different water depths are given. If we take an example of a wave period 10 seconds, and the wavelength decreases with the decrease of the water depth. See this curve here. Based on the dispersion relation, we can also calculate the phase velocity of wave given by this direct physical definition for the phase velocity as the wavelength divided by the wave period. Using the relations between the wave number and the wavelength and the wave frequency and the wave period, we can obtain another definition for the phase velocity given by this omega divided by k. If we employ the dispersion relation, we can calculate the phase velocity given in this. So if we compare the phase velocity in finite water depths to the phase velocity in deep water, we can see the difference. So the ratio of the phase velocity to the phase velocity in deep water is given as this, and the curve for the ratio of the phase velocity in finite water depths to the phase velocity in the deep water. So this ratio has a similar form as that curve of the wavelength, and it decreases with the decrease of the water depth. And based on the dispersion relation, we can also calculate the group velocity, which is defined by the differentiation of the wave frequency omega to the wave number as this. How this group velocity is derived, please refer to my previous talk, linear wave theory. So if we employ the dispersion relation, we can obtain the group velocity in the finite water depths given as this. Again, we can compare this group velocity with the group velocity in deep water. We can see the group velocity in finite water depths is much more complicated than that in the deep water. And the ratio of the group velocity Vg over Vg0 is given in this formula. And we draw out the ratio of the group velocity, and we can see the curve would be quite different from the previous curve. The ratio of the group velocity would increase first when the water depth decrease, and after a certain point, the ratio would decrease with the decrease of the water depth. The reason for this is because the ratio of the global velocity is comprised of two parts, the part in the square bracket and the part of the ratio of the wavelength. Whether the ratio of the global velocity is increasing or decreasing, it depends on these two parts. Here, an example is given for a wave of period 10 seconds in a water depth h equals to 20 meters. The example is for calculating the wavelength and wave velocities and compare to those in deep water. So for the wavelength in the finite water depth, the iteration method can be used for the dispersion relation, and we can obtain the wave number k and wavelength lambda. Here we can see the wavelength is 121.17 meters. So compared to the same wave in deep water, the wavelength is 156 meters, and the wave number k0 is 0.04. The wave phase speed Vp for the wave in the finite water depth is given as the wavelength divided by the period. So it is 12.117 meters per second. Compared to the wave phase velocity in deep water, it is 15.6 meters per second. The difference is minus 22.33%, means the phase velocity in the finite water depth is 22.33% smaller than the wave speed in the deep water. The wave global velocity Vg is calculated in this formula. It is 9.27 meters per second. Compared to the wave global velocity in deep water, Vg0, it is 7.8 meters per second. So the difference is 18.84%. This means the wave global velocity in the finite water depth in this case is larger than the wave global velocity in the deep water by 18.84%.